making use of latent energy in operational hydraulic infrastructure. Energy and water are basic resources for humans. They are closely linked. Large amounts of water are required to produce energy, and energy is consumed in the treatment and distribution of water. Thus, coordinated management of both resources is needed in order to not only reduce energy consumption in water management, but also reduce water consumption in energy production and recover the latent energy in circulating water in the form of hydroelectricity. The latter implies the development and construction of hydroelectric mechanisms adapted to the existing kinds of infrastructure. Principally, infrastructure that could be used for generating hydroelectricity includes sewage treatment plants, water purification plants, drinking water supply networks, irrigation canals, canals for hydroelectric power stations, and installations for the catchment and discharge of water in riverbeds and the sea. The large number of installations of this type imply great development potential for hydroelectric energy generation. Entities managing hydraulic infrastructures interested in exploiting their hydroelectric potential should embark on the following steps. First step: design and dimensioning of the installation. Latest technological advances allow the use of virtually any type of hydraulic infrastructure. Depending on the specific conditions at each site, the corresponding dimensioning and design of the installation must be carried out in order to optimize energy use. Choosing the correct type of hydroelectric generation technology is crucial. This is largely conditioned by parameters such as the gradient, the amount of flow to be tapped, the turbine performance curve, and the associated costs. Simply put, the criteria governing the use of the main commercial turbine models dictate Kaplan turbines for small gradients with medium to high flow rates, Francis turbines for bigger gradients with moderate flow rates, Pelton or Turgot turbines for large gradients with low flow rates, and hydrodynamic screws for small gradients with limited flow. Second step: securing licenses and permits. In general, the administrative processes required for these projects comprise the modification of the water concession, an authorization for the installation of electromechanical equipment and lines, an application to access and connect to the electricity network, obtaining an environmental impact study, inscription in either the Administrative Register for Electricity Production Plants or in the Register for Auto Consumption, and obtaining construction and activity licenses. Third step: execution of the works and installation startup. Depending on the particular conditions of the site and the chosen hydraulic technology, the associated works may be larger or smaller. Some of the actions normally required are staking out the terrain, creating access, excavating the ditches for hydraulic pipes and power lines, laying pipes or channels, putting up power lines, assembling the electromechanical equipment, and constructing storage facilities or buildings to house equipment. Fourth step: operation and maintenance. Once the installation is operational, it needs to be managed in a way that will optimize its potential. It is important to bear in mind that the plant where it will be located was intended for other uses, so that the generating unit needs to be taken into account along with the maintenance tasks and operational programs of the facility. With regard to the operational control of the installation, the devices are fully automated, allowing them to be monitored from a control panel to ensure operation under optimal conditions, manage energy flow, and generate actions in response to any anomalies. Apart from operational control, the generating facility also requires dedicated administrative management to monitor funds received from electricity companies for energy sold to the grid, as well as the payment of taxes and fees or the purchase of insurance. Regarding maintenance, a preventative maintenance program as well as a protocol for corrective maintenance actions in the event of failures or breakdowns must be drawn up in accordance with the maintenance plan of the installation. There are numerous examples of good practices for the exploitation of existing hydraulic infrastructures, both European and Spanish. One of them is the Hydroelectric project, whose objective is the validation of a unit specifically configured for use in water supply and distribution networks. It is a small, modular unit that is installed in place of pressure valves to generate electricity. It has been developed by a consortium comprising the Prodintec Technological Center, the City of Mieres, the companies Ingeniería de Manutención Asturiana S.A. and Servoship S.L. and the Asturian Energy Foundation. The project is co-financed by the European Commission through the Life Plus program. The wider use of initiatives such as the Hydroelectric project will help to consolidate a new, more sustainable water energy management model, favoring decentralized electricity generation while reducing polluting emissions and reducing pressure on the water supply.